All right, let's go ahead and get started here with our slideshow. Today's topic is minerals and how they develop a charge in solution. Let me get my pen. Okay. Imagine, if you will, we've got a ball mill that's grinding quartz, SiO2. There's water present as well in the ball mill. And as the ball mill grinds away, producing new surface area and reducing the particle size, there's going to be a plane of fracture developed on the quartz, shown here by the dashed line and the red line. So we're going to create new surface area, and in that process we're also going to create broken bonds, which result in surface charge on the new surface, on the newly created surface. So we've got a cation here associated with unsatisfied silicon on the surface. We've got an anion, or negative charge, associated with that oxide, unsatisfied oxide bond. We're going to show this as a chemical equilibrium, so there's water present with these newly created surface. And we know that with an equilibrium reaction, there's a forward and backward reaction, shown here. And the interaction then, or the chemical reaction of our surface with water, will result in a neutral surface, forming two hydroxide bonds on the surface. We call this a hydroxy bond, OH, two of those on the surface. So this can go forward or backward. The right hand side is a neutral surface. In other words, there's no charge associated with. The left hand side, of course, has both the cation charge, which is positive, and the anion charge, which is negative. Let's look at another reaction, taking this neutral surface now in the presence of hydrogen ion. So here's our neutral surface, once again shown as a chemical equilibrium, and one of these hydroxy surfaces can liberate a hydrogen ion, as shown here. And in both cases, both the reaction number 1 here and in reaction number 2, there's chemical equilibrium, and there's a mass balance maintained. In other words, the balance is reaction. All hydrogen ions, hydroxide ions are accounted for. It balances. But this second reaction here is quite interesting, because what it tells us is that we can add acid to the system, which would give us a high concentration of hydrogen ion. And we know from freshman chemistry that will cause the reaction to move in the opposite direction. In this case, adding acid will help to neutralize the surface. And so that's our first clue, really, that the influence of acid and pH might have on developing the charge on mineral surfaces in water. So as shown here, this statement: minerals can develop a surface charge that can be modified via ions in solution. In this case, for oxide minerals, we can add hydrogen, and of course we could actually add hydroxide ion too, because of the equilibrium reaction between hydrogen ion, hydroxide ion, and water. Having some trouble advancing. I was trying to go back when I needed to go forward. Sorry about that delay. So now let's take a bigger view of our mineral surface, and let's talk through that here. We've got our solid surface. This could be a mineral surface here, shown in the cross-hatched. We've got different labels. A, this is going to be our surface charge that the minerals developed. We give that the symbol chi naught, shown here. There's a diffuse layer of atoms that exist that in solution that will be needed to neutralize that surface charge, psi naught, chi naught. And these ions in solution are typically called counter ions or potential determining ions, or counter ions. There's different components to this diagram. There's, of course, the surface charge A. There's what's called the Stern layer, which is this layer of anchored ions right on the surface. In this case, there's two cations that reduce the surface charge, and then there's this diffuse layer of counter ions that further bring chi to 0, some distance away from the surface. So that comprises what we call the electrical double layer. Which we'll abbreviate the EDL, the electrical double layer. And there's 3 components to the electrical double layer. There's our surface charge, which we call chi naught. In the drawing, it's section A. B is the so-called Stern layer. And we define the Stern layer as the closest approach of adsorbed ions. The charge at the Stern layer we call the zeta potential. The specific charge at the Stern layer called the zeta potential. The third component of the electrical double layer are those diffuse ions. In total, those three components represent the electrical double layer. There we go. We're back. Those 3 components comprise the electrical double layer, the surface charge, the Stern layer, and the diffuse ions. Let's go back and take a look at those. So we've got the at the Stern layer, this would be the zeta potential then. And then the charge is fully neutralized only when we get some distance away from the surface. The point here is the electrical double layer balances the surface charge and consists of those 3 components: the surface charge, the Stern layer, and the diffuse layer. So what does this look like around a mineral? And this cartoon shows that we've got our particle, in this case with a negative surface charge. It will attract positively charged ions then to neutralize that negative surface charge. So we've got negative surface charge on the mineral. And of course, that depends on the solution pH, going back to our original drawing. We've got our stern layer showing those anchored ions that partially neutralize the surface. And then we've got our diffuse layer, which fully neutralizes that surface. So here's our definition of the zeta potential. Just outside of that stern plane, or sometimes at the stern plane, and it can approximate the surface charge, and that's an important point. The zeta potential approximates the surface charge because psi naught is difficult to measure directly. So here's an experimental plot showing the zeta potential versus solution pH, showing that we can adjust the zeta potential and which approximates our surface charge as a function of pH. And this is fairly typical plot for oxide minerals. In other words, as you increase the pH, or the acid concentration increases, the surface becomes positive, as indicated by the zeta potential. As you increase the base or raise the pH, the system becomes negative. But there's a specific point here where there's a net neutral surface. That's a very important point that we call the point of zero charge. Or the PZC, the point of zero charge. That's where the mineral surface is net neutral. In other words, the positive and negative charges completely balance out. And we can control then the zeta potential and the surface charge by either raising or lowering the pH. Now this PZC is mineral specific. In other words, quartz will have a unique PZC, as will other minerals. So here's our definition then of PZC. It's a solution pH where the surface has a net neutral charge. Now other minerals, non-oxide minerals, can also develop a surface charge as well. But generally, we don't think in terms of acid and base chemistry because these are non-oxides and they won't have that same chemical equilibrium like quartz will. So we talk in terms of their PZC in terms of a component of the mineral itself. So for pH, we know is the minus log hydrogen ion concentration. So here's some new kind of twist on that. PBA would be the minus log concentration of barium ion in solution. And so something like barite, you could imagine zeta potential. Have have units of millivolts. Mineral can be positive or negative, and we can vary the concentration of barium ion in solution, and it'll develop a inverted S-shaped curve very similar to what we just saw for oxide minerals. So in this case, the PBA, or the minus log concentration of barium ion, would have a PZC of 6.7. So not only can we adjust the hydrogen ion concentration and adjust the charge on the mineral surface, we can adjust the concentration of ions that comprise the mineral and also adjust the surface charge on the mineral. Now, keeping in mind, we're not talking about hydrophobicity here. That'll come later. Right now, we're just looking at mechanisms in that electrical double layer, the electrical double layer, EDL, ways in which we can change the charge on the mineral. We'll see later that with that knowledge of surface charge, we can then begin to modify the surface in terms of its hydrophobic, hydrophilic character. So right now we're just looking at mechanisms to understand the surface charge, and the key point is that we can add ions in solution like hydrogen ion in the case of oxide minerals, or barium ion in the case of barite, and adjust that surface charge. Fluorite, which by the way is my favorite mineral, non-oxide, but we can adjust the calcium ion in solution, for example, and adjust its surface charge. So we have a lot of tools then that allow us to adjust the surface charge, specifically ions in solution. So let's think more specifically about the surface charge on oxide minerals. And we're going to focus it at room temperature, 298 K, and work in units of Kelvin. We recognize that the minus log concentration of hydrogen ion, sometimes it's called the activity of hydrogen ion, activity in our case is equal to the concentration of hydrogen ion. Minus log concentration is solution pH, and there's a way to calculate the surface charge for oxide minerals. Chi naught in units of millivolts. We come up with this constant 0.59, converting natural log to log. We have to use a factor 2.303, and R is the natural gas constant, T is temperature, Z sub I is the charge on the ion, in this case hydrogen ion. Let's break these down for you. R is the natural gas constant, T is temperature, Z sub I is the charge on the ion. In this case, we're interested in hydrogen ion, so Z is equal to 1. We're going to use units of calorie per degree for our natural gas constant. And this equation up here that says 2.303 times RT, we're at room temperature for Kelvin. Our hydrogen ion charge is 1. F is Faraday's constant. Just 23,060 calories per volt per mole gives us this 0.577 here. It actually should be 0.059 volts, and we can use our understanding of the logarithm and come up with an equation then to predict the surface charge on oxide minerals. The surface charge chi naught is equal to 0.059 from above times minus pH at the PZC minus the pH of the solution. So we can actually calculate the surface charge on oxide minerals. And in this table, we've listed oxide minerals as well as their surface charges. So, for example, SiO2 has a point of zero charge of 1.8. Something a little more basic like Al2O3 will have a point of zero charge of 9.1. Something, a mineral intermediate in its basicity, something like cassiterite, will have a PZC of 4.7, which gives rise to this concept of potential determining ions. These are ions that can change the surface charge for oxides. This includes the metal ion, the hydroxide ion, and hydrogen ions. Let's go back to that concept of potential determining ions. These are ions that can change the surface charge. So for something like fluorite, these would be calcium ion, fluoride ion. Something like SiO2 for oxides, silicon ion. Oops. I'd like to get rid of that. Oxygen anion. But for oxides, this also includes hydrogen ion and hydroxide ion, going all the way back to our original figure where we were showing the ability to change the surface charge of quartz by adding an acid or a base. For non-oxides, though, typically we look in terms of the ions. But all of these are examples of potential determining ion because we can change the surface charge by addition of these ions. So something like SiO2, which has a point of zero charge of 1.8, would have a charge versus pH curve that looks something like this, where 1.8 is our point of zero charge. So-called PZC. And we could draw similar curves. Let's go back here. Something like, for example, Al2O3 with a PZC of 9.1. Come in something like this. Its PZC would be 9.1. So we can adjust the surface charge by adjusting the acid or base in the system. Let's go all the way back here to our electrical double layer. So we've got our electrical double layer that consisted of that surface charge, the stern layer, which is a reflection of the zeta potential and is an indication of the, which we use as an indication of the charge, and the diffuse layer. But let's talk a little bit then about the thickness of this diffuse layer. How thick is it? We can control the double layer thickness through an understanding of this constant kappa. The double layer thickness is given by 8 pi f squared nu squared c divided by epsilon RT whole quantity to the 1/2 power. This is called kappa. The double layer thickness, which is equal to 1 over kappa, is the double layer thickness. F is Faraday's constant, nu is the valence of the ion, C is the molar concentration, epsilon is the dielectric constant, R is our natural gas constant, T is temperature in degree Kelvin. So for a 1,1 type salt, so we're adding sodium chloride, which is one of these ions. It's non-potential determining. Which usually we give the name a counter ion. In other words, they exist in solution but not at the surface. We can add counter ions, just salt to solution, and this double layer thickness equation tells us that as we add more and more salt, that concentration term C, the molar concentration, will go up and the double layer thickness will go down. And so this table here relates concentration of salt, in this case sodium chloride, to 1 over kappa, or the double layer thickness. So as we add more and more salt, that double layer gets pulled closer and closer to the surface. So we can control the surface charge, but we can also control the double layer thickness. In other words, we can pull this double layer closer and closer to the surface with increasing salt concentration. Which is, we'll see later, is an important ability. So we can control the charge through potential determining ions. We can control the thickness of the electrical double layer, or the diffuse layer, as well, by adding salt to the system. So we have a lot of control then of the electrical double layer simply by adding ions. So let's review a little bit. We've got the electrical double layer, EDL, consists of the surface charge. We abbreviate sign that. The stern layer. These are kind of anchored ions, usually potential determining ions. For oxides, this would be hydrogen ion, hydroxide ion. Oops, we need to flip the screen back. There we go. And at the stern layer, we approximate the zeta potential, which we'll use as an approximation for the surface charge, which is difficult to measure. And then we have our diffuse layer, which helps us to fully balance that surface charge, and these includes then these counter ions, sodium chloride ions. So that's the electrical double layer, as well as the type of ions that exist in the electrical double layer. 1 over kappa is the double layer thickness. We can control that with salt addition, these counter ions. We can pull that double layer closer and closer to the surface. So that's the other important concept is the point of zero charge, the so-called PZC for oxides. Typically get an inverse S-shaped curve, and the point of zero charge is where there's a net neutral surface. So we can add acid or base to get at that point of zero charge. So that's the main features of the electrical double layer, the components, as well as how we can control the electrical double layer.